My name is Fred Jackson from Strain Measurement Devices. We make sensors for medical devices. All of our sensors are non-invasive, meaning that the sensor does not come in contact with the fluid being measured. The sensor only comes in contact with the disposable set. The sensors include occlusion, air in line, liquid level, scales for weighing reagent bottles or flow, microfluidic sensors, and what we're going to talk about today are flowmeters. Just a brief outline of what I'm going to talk about. First, we're going to talk about the operating principles. Then we're going to look at two traditional flow meter designs. We're going to look at SMD's non-invasive transducer. Then we're going to talk about system architecture and signal processing. And we're going to finish up with experimental results from a peristaltic pump. In traditional transit time flow meters, there are two techniques. There's a diagonal mode and a V mode. And the transducer on the left, which is the yellow thing, is called the upstream transducer. The one on the right is called the downstream transducer. And basically what you're doing in a transit time flow meter is you're sending a pulse in the downstream direction and then shutting that off and then sending a pulse in the upstream direction, and the time difference is proportional to flow velocity. If you look at the equation on top, delta T is equal to the upstream time minus the downstream time, and the terms in that, for all of you that are mathematically inclined, the L is the acoustic path length from one transducer to the other. V is the velocity of the fluid in the tube. C is the speed of sound in the fluid at the particular temperature where you're measuring it, or as we call it, acoustic velocity. And because C is much larger than V, that simplifies to the equation on the right. So to calculate velocity, basically you have L times delta T over 2 cos theta TU TD. The operative thing there is that L is the most important factor. One of the disadvantages of this flow meter design is that the acoustic path length is very small, usually only a few tube diameters long. And as a result, the time being measured is a very short time, which requires expensive electronics. Another flow meter design uses what's called a U-shaped tube, and there's a transducer at each end of that tube. This is a much more accurate system, but there are a couple disadvantages here. One is that the tube itself needs to be part of the disposable set, so you need to manufacture an expensive component in your disposable set in order to get a reading. And secondly, there's a large pressure drop because there are multiple changes in direction of the flow. SMD's ultrasonic transducer eliminates a lot of these problems. The way this thing works is the operator, usually a nurse or technician in an operating room, whatever, is all they have to do is just press the tubing into the slot, which takes a second or two, so that it's a dry coupling. It doesn't require any acoustic gel, and it also offers us to make virtually an infinitely long acoustic path length. As long as we have enough power to send the pulse that far down the tube, we can make the L much longer. So you'll see in a minute the kind of accuracy results that we've been getting. Just briefly, system architecture and signal processing. The digital signal processor, DSP, is the brains of the system. It contains the clock, which controls all the functions, the signal conditioning, and calculates the flow velocity. The pulsar sends out a 15-volt square wave pulse first to the upstream transducer and then to the downstream transducer, and that's switched by the high voltage switcher. The transmit and receive switch then alternately takes the signal from the receiving transducer, amplifies it at a 20 hertz rate, does an A to D conversion, and then stores the instantaneous waveform in the FIFO memory, which is then used by the DSP to calculate the flow velocity. That number is then stored in the memory for later analysis. And just a quick couple of numbers here. We say on this slide we can achieve a 0.2 nanosecond time accuracy measurement. We've now gotten significantly better than that, and so the numbers on this slide, which this presentation was first written about 7 months ago, we're able to achieve much better numbers. But at the time we said for a 1/4 inch OD tube, which had a 0.18 inch ID, where the centimeters about 4 inches or 10 centimeters away, the measurement accuracy is 1% at 200 ml per minute, 2% at 100 ml per minute. We're now able to achieve better than 1% at 100 ml per minute, and we think within a couple of weeks, we just got some new boards in, we'll be able to achieve close to 1% at 50 ml per minute. This is just characterization testing we did. The graph on the left was a laminar flow. We basically had a constant head of water and measured the flow rate and then flowed the liquid into a beaker on a scale, and were able to verify the exact flow over a period of time. And we could see there that the results show better than 1% is achieved. On the right-hand graph was pulsatile flow. So you'll see on the next slide what pulsatile flow looks like. Actually, I'm going to just flip to that in a second. So if you look at, say, the lower left graph, that's what a pulsatile flow looks like. So if you look at this graph on the right, what we're doing is we're integrating under that curve and measuring the flow rate over some period of time. I think in this case we did it over about 30 seconds to a minute. But what this graph shows is the green, I don't know if you can tell they're green, but they're triangles are the actual settings. This happened to be a dialysis machine, rotary peristaltic pump. There were the settings on the dial, and the red line is the scale measurements. We flowed into a beaker on a scale and weighed the liquid, and the blue are the flow meter outputs. So what we're able to show there is that even with the highly pulsatile flow over a short period of time, we were able to achieve better than 3% accuracy. And again, that's now greatly improved. That's probably about 1.25% right now, and we think we can do a little better. These are actual outputs from 4 different flow settings on the rotary peristaltic pump, which again was a dialysis pump. You might wonder why we did 0 flow. There are a couple reasons why a user might want to do that. One is to verify that the sensor is working. If the sensor doesn't read 0 and you know there's no flow, so it can be used diagnostically. It can also determine if the tube set is properly installed in the peristaltic mechanism. The second flow rate, just an interesting note on that, if you notice during the single cycle, the flows actually go negative for about 0.2 seconds in a 2-second waveform, and our customer was not aware that that was happening. What that turns out to be is as the cam in the rotary mechanism comes off the tube expands out, creates a negative pressure in the tube, and actually sucks the liquid back. So the result of that is that fluid is actually flowing in the negative direction. The other waveforms, we could talk about those all day, and you could analyze them and talk about them. But one of the interesting things is by looking at that waveform and comparing that to what's in memory, you can determine if the tube's improperly installed, if the tube has been stretched out, You know, all kinds of other things might change that waveform. So there are a lot of diagnostics that one can do by looking at the waveforms that come out of this. I believe in this case we were measuring at about 150 samples per second of actual calculated flow rates. In summary, an ultrasonic flow meter has been developed and is now being sold, which can be used to measure non-invasive flows in medical disposable sets. We can achieve very high accuracy and repeatability, and it's getting better every day over a large dynamic flow range. The output of the flow meter can be either instantaneous flow, like you saw in the graphs a minute ago, or we can give you cumulative flow over a period of time, which is what most people are interested in. Or it can output both. So you can use one for diagnostics and the other for you know, determining the cumulative flow over a long period of time. And lastly, our customers have told us that they've got two main applications. One is for closed loop control. So you remember in the earlier graph, the guy set the curve on, or the dial on his pump to, say, 400 ml per second, and he was actually getting out about 340. So the flow meter could be used to directly close the loop, or it can be used increasingly. Hospitals and device manufacturers are asking us for devices to verify output of their medical devices, either pressure or bubble size or flow rates. So there's an awful lot of interest in using this sensor for verification for legal and other reasons in a hospital. So that concludes our presentation. We are in booth 2253. If anyone has any discussions that they'd like to have with us, 2253. Are there any questions? Thank you very much.